Welcome to this problem walkthrough. In today's session, we'll explore problem number 1230, toss strange coins. We'll break down the problem, analyze different approaches, and work toward an efficient solution. Let's dive in. In this problem, you're given a set of coins, where each coin has a specific probability of showing heads when tossed. The task is to determine the probability that exactly a certain number of these coins, denoted as the target, will show heads. The input consists of a list called prob, where each element represents the probability of a particular coin showing heads, and an integer target, which specifies the exact number of heads we need. The output is a single floating point number, representing the calculated probability of achieving this target. To illustrate this, let's look at some examples. In the first example, we have a single coin with a probability of 0.4 showing heads, and the target is 1. The output in this case is 0.4. This is because there is only one coin, and the probability of getting exactly one head is simply the same as the probability of that coin showing heads, which is 0.4. Now, let's consider a slightly more complex example with two coins. Here, we have two coins, each with a probability of 0.5 of showing heads, and the target is one head. To achieve this, there are two possible scenarios. In the first scenario, the first coin shows heads while the second coin shows tails. The probability of this happening is 0.5 multiplied by 0.5, which equals 0.25. In the second scenario, the first coin shows tails while the second coin shows heads. Again, the probability for this is 0.5 multiplied by 0.5, giving 0.25. Adding these two probabilities together, we get 0.25 plus 0.25, which equals 0.5. Now, let's explore an example with three coins. In this example, we have three coins with probabilities of showing heads as 0.3, 0.6, and 0.8 respectively. The target is to get exactly two heads. There are three ways this can happen. First, coins 1 and 2 show heads while coin 3 shows tails. Second, coins 1 and 3 show heads while coin 2 shows tails. And third, coins 2 and 3 show heads while coin 1 shows tails. By calculating the probability of each of these scenarios and summing them up, we find the total probability to be 0.288. This problem also includes some constraints and edge cases to consider. For instance, if the target is 0, it means all coins must show tails, and if the target equals the number of coins, all coins must show heads. Additionally, if all probabilities are 0 or 1, the results will depend on whether the target aligns with these extreme cases. These details help guide the implementation and handle special scenarios effectively. To approach the problem, we first consider a brute force method. The intuition here is to generate all possible outcomes of tossing the coins and count the cases where the number of heads matches the target. With n coins, each coin has two possibilities, heads or tails, leading to 2n total outcomes. For each outcome, we calculate the probability of that specific sequence and check if the number of heads equals the target. While this approach is straightforward and conceptually simple, its computational cost makes it impractical for larger values of n because the number of outcomes grows exponentially. Key observations include the fact that for each coin, the probability of it landing heads is given as prob I, while the probability of tails is 1 prob I. However, computing the probabilities for all 2n outcomes quickly becomes infeasible as n increases. With a time complexity of 2 to the power of n, this approach is not scalable for large inputs. Therefore, we turn to an optimized method using dynamic programming. Here, we define dp I, k, as the probability of achieving exactly k heads after considering the first I coins. This significantly reduces the computational burden by avoiding the need to explicitly generate all possible outcomes. The dynamic programming approach relies on a state transition to calculate probabilities incrementally. If the ith coin lands heads, its probability contributes to the target as dp I, k, plus equals dp I1, k1, asterisk prob I1. If the coin lands tails, the complementary probability is added as dp I, k, plus equals dp I1, k, asterisk 1 prob I1. The base case starts with dp 0, 0 equals 1, indicating that the probability of getting 0 heads with 0 coins is certain. For all other cases where k greater than 0, we initialize dp 0 k equals 0 because it is impossible to achieve heads without any coins. A key observation here is that to compute the current row of the DP table, we only need the values from the previous row. This allows us to reduce space complexity by using a rolling array, where we overwrite the previous row as we compute the current one. This optimization reduces the problem size and improves efficiency. As a result, the time complexity is proportional to O, an asterisk target, and the space complexity can be reduced to O, target. An alternative approach involves using a recursive depth-first search with memoization. Here, for each coin, we recursively decide whether it contributes to meeting the target number of heads. Memoization stores intermediate results to prevent redundant calculations, ensuring the solution remains efficient. Although the recursive DFS with memoization is equivalent to the dynamic programming solution in terms of time complexity, it introduces stack overhead and is less intuitive for iterative implementations. Among the approaches considered, the dynamic programming method stands out as the most efficient and intuitive solution. It leverages the incremental nature of coin tosses, building the solution row by row without the need to explore all possible outcomes explicitly. This avoids the exponential growth inherent in the brute force approach. Compared to the recursive DFS method, dynamic programming eliminates stack overhead and is easier to debug and optimize. Each approach comes with trade-offs. The brute force method is simple but computationally infeasible for large inputs. The recursive DFS approach is elegant but suffers from stack limitations. Dynamic programming, on the other hand, achieves an optimal balance between efficiency, clarity, and scalability. The key insight, or the aha moment, was realizing that we could compute probabilities incrementally using dynamic programming, reducing the complexity from exponential to polynomial time. Furthermore, the use of rolling arrays to minimize space complexity makes this approach even more effective for handling large inputs. Therefore, the dynamic programming approach is chosen for its clarity, efficiency, and ability to scale well with input size. To solve this problem, we need to determine how many ways we can achieve exactly k heads when tossing in coins, where each coin has an equal probability of landing heads or tails. The brute force approach tackles this by systematically generating all possible outcomes of tossing these coins. Each outcome is evaluated to check whether the number of heads matches the target k. To break this down, we first define our input parameters, n, representing the total number of coins, and k, the desired number of heads. Then, we generate all possible outcomes of tossing in coins. Since each coin has two possible outcomes, heads or tails, the total number of outcomes is 2n. These outcomes can be represented as binary sequences of length n, where a 1 indicates a head and a 0 indicates a tail. For example, the sequence 101 means the first and third coins landed heads while the second landed tails. This systematic enumeration forms the basis of the brute force approach. Once we have the outcomes, the next step is to count how many of them meet our target condition. To do this, we initialize a variable, count, and set it to 0. This variable will track the number of valid outcomes, those where the number of heads equals k. We then iterate through all 2n binary sequences. For each sequence, we count the number of 1s, which represents the number of heads. If this count matches the target k, we increment our count variable by 1. After evaluating all outcomes, the value of count will give us the total number of valid outcomes, which we return as the result. For clarity, the pseudocode shows the steps in detail. We loop through integers from 0 to 2n1, convert each integer to its binary representation of length n, count the 1s in the binary string, and compare that count to k. If it matches, we increment count. This approach ensures we systematically evaluate every possibility. This brute force method highlights some important insights about the problem. First, the number of outcomes grows exponentially with the number of coins, n, because there are 2n possible sequences. This rapid growth makes the brute force approach computationally expensive for larger values of n. Second, using binary representation is a powerful way to handle these outcomes. Each sequence corresponds to an n-bit binary number, and this representation allows for efficient generation and manipulation of the outcomes. Third, the operation of counting 1s in a binary string is central to validating an outcome, as it directly corresponds to counting heads. Additionally, we must consider edge cases. For example, if k is 0, the only valid outcome is all tails, represented as 0, 0, 0, 0. If k equals n, only the all-heads sequence, 1, 11, 1, is valid. And if k is greater than n, it's impossible to achieve, so the result is always 0. These insights help us understand the strengths and limitations of this approach. The data structures and optimizations we use can significantly improve the efficiency of solving this problem. For data structures, integers are ideal for representing outcomes in binary form. For example, the integer 5 can represent the sequence 10143 coins. Binary operations, such as bit shifting, allow for efficient generation and manipulation of these outcomes. Additionally, a single integer counter, count, is sufficient to track the number of valid outcomes. To optimize the brute force approach, we can use pruning. This means stopping early when it becomes impossible to achieve k heads, such as when the number of remaining coins is fewer than the heads we still need. Another powerful optimization involves using the combination formula C n k equals n slash k asterisk nk to directly compute the number of valid outcomes without generating all sequences. This approach reduces the computational complexity from exponential to linear, making it far more efficient for larger inputs. Finally, let's analyze the complexity of these approaches. For the brute force method, the time complexity is 2 to the power of n asterisk n. This accounts for generating 2 n outcomes and counting the 1s in each binary sequence, which takes n time per sequence. The space complexity in this approach is n, because we need to store the binary representation of each sequence. In contrast, the optimized approach using the combination formula has a time complexity of n, as computing the factorial values for c, n, k involves only linear operations relative to n. The space complexity is reduced to 1, since we no longer need to store any intermediate binary sequences or outcomes. This significant reduction in both time and space requirements makes the optimized approach highly suitable for larger values of n, while still maintaining the ability to solve the problem accurately and efficiently. This solution uses dynamic programming to solve the problem of calculating the probability of obtaining exactly target heads when tossing in coins, each with a unique probability of landing heads. Explanation. 1. Initialization. The DP table is a 2D list where DP, I, j, represents the probability of getting exactly j heads when considering the first I coins. The table is initialized to zeros, except for the base case DP, 0, 0, equals 1, which signifies that with 0 coins, the probability of 0 heads is 1. 2. Filling the DP table, we iterate through each coin, from 1 to n, and each possible number of heads, from 0 to target. For each combination, we compute the probability as a sum of 2 scenarios. If the current coin is tails, the probability is dp, I1, j, asterisk, 1 prob, I1. If the current coin is heads, the probability is dp, I1, j1, asterisk prob, I1, only valid if j greater than 0. 3. Result extraction. After filling the table, the value dp, n, target, contains the desired probability of getting exactly target heads using all n coins. Complexity. Time complexity, n asterisk target, where n is the number of coins in target is the maximum number of heads. Space complexity, n asterisk target, for the DP table. Edge cases. If target is 0, the function correctly handles the probability of no heads. If target exceeds the number of coins, the probability is 0. If all probabilities are 0 or 1, the solution adapts seamlessly. This implementation is efficient, concise, and directly addresses the problem requirements. Here, we begin with the Java implementation of the problem toss strange coins. The solution uses dynamic programming to calculate the probability of getting exactly the target number of heads when tossing the coins. First, we initialize a 2D array called dp with dimensions of n plus 1 by target plus 1, where n is the number of coins. This table will store the probabilities for different combinations of coins and heads. The base case is defined as having 0 coins and needing 0 heads, which has a probability of 1, so we set dp 0, 0 to 1.0. Next, we use a nested loop to fill the DP table. The outer loop iterates over each coin, and the inner loop goes through the possible numbers of heads, from 0 to the target. For each combination of coin and head count, there are two scenarios to consider. The current coin can either land tails, which keeps the number of heads the same, or it can land heads, which increases the head count. The probability of the coin landing tails is multiplied by the value in the DP table for the same number of heads at the previous step. Similarly, if the coin lands heads, and the number of heads is greater than 0, we add the corresponding probability from the previous step, scaled by the coin's probability of landing heads. This way, the table is updated dynamically for all combinations. Finally, after filling the DP table, the result is found at DP, n, target, which represents the probability of getting exactly the target number of heads after tossing all the coins. This value is returned as the final result of the function. By breaking the problem into smaller subproblems and using dynamic programming, this implementation efficiently calculates the desired probability while avoiding redundant computations. To solve this problem, we need to calculate the probability of getting exactly 2 heads when tossing 3 coins, each with a probability of 0.5 for heads. We start by initializing a dynamic programming table, or DP table, where the dimensions are based on the number of coins and the target number of heads. Here, n is 3 since we have 3 coins. The table is initialized with zeros, except for the base case DP, 0, 0, equals 1, which represents the probability of having 0 heads with 0 coins. The table is structured so that rows represent the number of coins used and columns represent the number of heads achieved. Initially, the table looks like this. The first row has 140 heads, and all other entries are zeros. Next, we start filling this table by iterating through each coin and the possible number of heads achieved so far. When considering the first coin, the probabilities for 0 and 1 head are calculated. For j equals 0, meaning 0 heads, the probability is dp 1, 0 equals dp 0, 0, asterisk 1 to 0.5, which evaluates to 0.5. For j equals 1, meaning 1 head, the probability is dp 1, 1 equals dp 0, 0, asterisk 0.5, which also evaluates to 0.5. This updates the table, where the second row now shows probabilities of 0.5 for 0 heads and 0.5 for 1 head. Next, considering the second coin, we calculate the probabilities for 0, 1, and 2 heads. For 0 heads, dp 2, 0 equals dp 1, 0, asterisk 1 to 0.5, resulting in 0.25. For 1 head, the probability combines contributions from the first coin and the second coin, calculated as dp 2, 1 equals dp 1, 0, asterisk 0.5 plus dp 1, 1, asterisk 1 to 0.5, which equals 0.5. For 2 heads, the calculation is dp 2, 2 equals dp 1, 1, asterisk 0.5, resulting in 0.25. These updates give us a table where the second row is refined with probabilities for all possible outcomes. Now, we consider the third coin. For 0 heads, the probability becomes dp 3, 0 equals dp 2, 0, asterisk 1 to 0.5, which evaluates to 0.125. For 1 head, the combined probability is dp 3, 1 equals dp 2, 0, asterisk 0.5 plus dp 2, 1, asterisk 1 to 0.5, which results in 0.375. For 2 heads, the probability is dp 3, 2 equals dp 2, 1, asterisk 0.5 plus dp 2, 2, asterisk 1 to 0.5, also 0.375. After these calculations, the final table is complete, and the value at dp 3, 2, which corresponds to 3 coins and exactly 2 heads, is 0.375. This tells us that the probability of obtaining exactly 2 heads with 3 coins, each with a probability of 0.5 for heads, is 0.375. In the next example, we calculate the probability of getting exactly 1 head when tossing 2 coins with probabilities of 0.3 and 0.6. First, we initialize a DP table. Since there are 2 coins, the table will have 3 rows and 2 columns. As always, the base case is set with dp 0, 0 equals 1, representing 0 heads with 0 coins. All other entries are initially 0. Now, for the first coin, we calculate the probabilities for 0 and 1 head. For 0 heads, dp 1, 0 equals dp 0, 0, asterisk 1 to 0.3, which evaluates to 0.7. Then, for one head, the probability is dp 1, 1 equals dp 0, 0, asterisk 0.3, which equals 0.3. These calculations update the table so that the second row now reflects the probabilities for using the first coin. Next, we consider the second coin. For 0 heads, the probability is dp 2, 0 equals dp 1, 0, asterisk 1 to 0.6, which evaluates to 0.28. For one head, the combined probability is dp 2, 1 equals dp 1, 0, asterisk 0.6 plus dp 1, 1, asterisk 1 to 0.6, which equals 0.54. After updating the table, the final row now reflects the probabilities for using both coins. The value at dp 2, 1 represents the probability of getting exactly one head with two coins, and it is 0.54. Finally, in the last example, we calculate the probability of getting 0 heads when tossing 3 coins with probabilities of 0.4, 0.8, and 0.2. We initialize the DP table with 4 rows and 1 column, since the target is 0 heads. As always, the base case is set with DP 0, 0 equals 1. For the first coin, the probability of 0 heads is dp 1, 0 equals dp 0, 0, asterisk 1 to 0.4, which evaluates to 0.6. For the second coin, the probability is dp 2, 0 equals dp 1, 0, asterisk 1 to 0.8, which equals 0.12. Finally, for the third coin, the probability becomes dp 3, 0 equals dp 2, 0, asterisk 1 to 0.2, resulting in 0.096. This gives us the final probability of attaining 0 heads, which is 0.096. The time complexity of this solution comes from the nested loops used to populate the dynamic programming table. First, we have an outer loop that iterates over all the coins, which means it runs from 1 to n, where n is the total number of coins. This gives us n iterations. Inside this, there's an inner loop that iterates over the possible number of heads, from 0 to target, resulting in target plus 1 iterations for each coin. For every cell in the DP table, we perform a constant amount of work, including probability calculations and additions, which is 1. When we combine these, the total time complexity becomes n asterisk target plus 1 asterisk 1, which simplifies to n asterisk target. This shows that the time complexity grows linearly with both the number of coins and the target number of heads. The space complexity of the solution is determined by the memory used to store the dynamic programming table and the additional variables. The DP table has dimensions, n plus 1 x target plus 1, because it stores results for all coins and all possible numbers of heads up to the target. This requires space proportional to n plus 1 asterisk target plus 1, which simplifies to n asterisk target. Alongside this, we use a constant amount of space for variables such as n, prob, target, I, and j, which contributes 1 to the overall space usage. When we combine these, the total space complexity becomes n asterisk target plus 1, which simplifies to n asterisk target. This means the DP table dominates the memory usage in this solution. In terms of best, average, and worst-case scenarios, the complexity remains consistent because the algorithm always processes all cells in the DP table. In the best-case scenario, even if the probabilities or target values are favorable, the algorithm still iterates through all n asterisk target cells to fill the table. Similarly, in the average and worst-case scenarios, the algorithm's structure does not change, it always performs the same number of operations regardless of the input distribution. Therefore, the time and space complexities are always n asterisk target, no matter the input. To better understand the efficiency of dynamic programming, we can compare it to a brute force approach. A naive method would involve simulating all possible outcomes of n coin tosses and counting the cases where the number of heads equals target. Since there are 2n possible outcomes of n coin tosses, the time complexity of this approach is 2 to the power of n. On the other hand, the brute force approach has constant space complexity, 1, as it only requires a few variables to keep track of the outcomes. In contrast, the dynamic programming method avoids simulating all outcomes by reusing the results of subproblems. While this increases space usage to n asterisk target due to the DP table, it dramatically reduces the time complexity to n asterisk target, making it far more efficient for larger inputs. To conclude, the mathematical proof of the dynamic programming approach's big O complexity reinforces its efficiency. The time complexity arises from the DP table, which has n+1 asterisk, target +1 cells, each processed in constant time. Therefore, the total time is proportional to the product of n target. Similarly, the space complexity is dominated by the DP table, which requires n+1 asterisk, target +1 cells. This proves that the algorithm has polynomial time complexity and manageable space usage. Compared to the brute force method, which has exponential time complexity, the dynamic programming solution provides a significant improvement for handling larger inputs effectively. When solving the toss strange coins problem, there are a few common mistakes that can trip you up if you're not careful. First, let's talk about recursive solutions. A common error is failing to define the correct base case. Without a clear base case, like when the target number of heads reaches 0 or when there are no coins left to process, the recursion can either run indefinitely or produce incorrect results. Next is an issue specific to dynamic programming: double counting. This happens when overlapping subproblems aren't handled properly, often because memoization isn't implemented. As a result, you may end up recalculating the same states repeatedly. Another frequent mistake is misunderstanding the difference between probability and counting outcomes. For instance, if the task involves probabilities, it's not enough to count the possible outcomes, you must divide by the total number of possibilities, which is typically 2 raised to the power of the number of coins. Finally, brute force approaches are straightforward but inefficient for larger inputs. With n greater than 20, the number of outcomes grows exponentially, making it impractical to solve without optimization through dynamic programming or combinatorial methods. Now, let's consider edge cases and some insights for interviews. Ignoring edge cases is a common pitfall. For example, what happens if there are no coins at all? Or if all tails are a valid outcome? Another tricky scenario is when the target number of heads exceeds the total number of coins. These are situations that must be accounted for to ensure correctness. From an interview perspective, recognizing patterns is key. Many coin toss problems are variations of subset, permutation, or combination problems. By identifying this, you can apply well-known formulas instead of relying on brute force. Additionally, interviewers often look for your ability to justify your approach. For example, explain why dynamic programming is better suited than brute force in terms of time and space complexity. It's also a good idea to test edge cases early in your solution to demonstrate robustness. And if you're using dynamic programming, be sure to clearly communicate what your DP table represents and how the transitions between states occur. For example, you might explain that DP I, J represents the number of ways to achieve J heads using the first I coins. This level of clarity is crucial during interviews. There are also several related problems on LeetCode that share similarities with toss strange coins, and practicing those can strengthen your understanding. For instance, LeetCode 416, partition equals subset sum, has a similar dynamic programming structure where the goal is to determine if subsets can meet a specific target. Then there's LeetCode 494, target sum, which involves assigning positive and negative signs to elements to achieve a target sum. This is quite analogous to flipping coins to meet a head count. LeetCode 377, combination sum 4, focuses on counting combinations, which can be adapted to problems involving probabilities, like this one. Finally, LeetCode 322, coin change, is another DP problem where you calculate combinations to meet a target. These problems not only reinforce the techniques needed for toss strange coins but also broaden your toolkit for tackling variations on this theme. Now, let's compare alternative approaches and their trade-offs. Starting with brute force, it's the simplest to implement but has exponential time complexity, 2 to the power of n, making it suitable only for small inputs. Dynamic programming is more efficient, reducing the time complexity to an asterisk target, but it does require extra space for the DP table. Combinatorics, on the other hand, can offer an even more efficient solution for certain variations if you have a solid understanding of how combinations work. However, it may not fit all problem constraints, especially when the problem is more nuanced. Backtracking is another option, which is great for exploring all valid combinations. However, it tends to be slower than dynamic programming for larger inputs since it doesn't optimize overlapping subproblems. Each approach has its strengths and weaknesses, so the key is to choose the one that best balances simplicity and efficiency for the given constraints. That brings us to the end of this walkthrough. To summarize, we explored problem number 1230, discussed key approaches, and highlighted important concepts like probability and optimization. Thank you for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!